Hello YouTube, I'm back from my rather long hiatus and I'm starting a new series where I present theorems that are pretty big in mathematics and I try to simplify them as much as I can. So in this video I'll be covering the Poincare-Bendixson theorem, which is a big result in dynamical systems. And what it basically says is if you take the Cartesian plane R2, so let's call this the Cartesian plane even though I know it's unbounded, then you take a bounded and closed subset omega of this Cartesian plane. So suppose that this blob over here is omega. It's closed off to the rest of R2 and it's bounded, so there's no going off to infinity. Okay, so now what is condition 2? Well, assumption 2 is you can define a continuous vector field on omega. Okay, so what the heck does that mean? Well, it means that if you take any point in omega, you can assign it an arrow or a vector. And what that vector does is it tells you where, if a particle was at that point, where it would go next if you move forward in time. So like, if you had a particle at this point over here, you let time elapse by 1 second, it would go this way. It would move in this direction. And you define an arrow, or you assign an arrow to every single point in this domain, omega. Okay? And so that would be a vector field, not necessarily continuous. Now, to explain continuity, I'll say that this equation here, x prime is equal to f of x, is actually shorthand notation for a 2D system of differential equations, which I'll write explicitly right here. Okay. So, oh, and by the way, f and g are continuous functions of x and y. Okay, so what that basically means is if you take, like, I don't know, any point, say you call that point 0, 0. So you have 0, 0, you can plug 0 and 0 into f and g, and for example, you'd be able to get the derivative of x and y with respect to time for that specific point. So dx dt would tell you at 0, 0 how fast in the right-left direction you're going, and dy dt at 0, 0 would tell you how fast you're moving in the up-down direction at 0, 0. So basically, if you know these equations, you know what point you're talking about. You can just plug the points in, get the arrow that you're looking for. So you have this for every single point in the region. And it's continuous so that, for example, if you have like a point that's really close to 0, 0, you wouldn't be having a sudden jump from like the upward arrow to just a downward arrow. If you have discontinuities, then that would disrupt a lot of the assumptions and this Poincare-Bendixson theorem might not work anymore. Okay, so you want to keep it continuous and you have a vector field, so every point gets an arrow. Perfect. Now, assumption 3 says that if you have omega, and assume it has no fixed points. Well, what does that mean? Well, mathematically, it means that dx dt and dy dt can never be 0 at the same time. So what that means in terms of geometric intuition, well, it means that there's no such thing as a point in this omega where there's no arrow. Or in other words, every single point inside this region must have an arrow that's telling it to move somewhere else as time goes forward. A point can never stay stationary at any given time. It must go somewhere else. Okay, good. It has no fixed points. Now, suppose that you have a starting point. So suppose that we take that same point, I guess 0, 0. Well, it has a vector assigned to it, and suppose that it, I don't know, you let it flow, and I don't know, goes to another point. We'll just call it like, I don't know, x1, right? Now, that point x1 in itself has a vector assigned to it. So say that it has a vector here, and so it goes to x2, and x2 itself has a vector, and so as you just let this thing flow forward in time, it creates this trajectory, which we'll call phi, and suppose that it's bounded within omega. Okay, and by the way, we're taking really tiny time steps because it's a continuous vector field. So we're taking very, very, very tiny time steps that are infinitesimally small. I don't know if I pronounced that correctly. And so one thing that us dynamical system people are very interested in is what is the behavior of phi as time goes to infinity. Because it's in this bounded region, it can't really go off to infinity or anything because it's bounded. So if there's nowhere to go for this trajectory other than staying inside omega, what can it do? And so the answer to that question is that it must approach a limit cycle. Okay, so what is a limit cycle? Well, first, to explain what a limit cycle is, I'll have to explain what a regular cycle is. So a regular old cycle is basically a trajectory where, first of all, let me just draw that omega again. I erased it in the cut, but basically, a regular old cycle is where you just have a trajectory that forms a loop, a closed loop, and it just, as time goes infinity, it just never stops oscillating in this fixed interval, or this fixed loop. Kind of boring, right? Now, what a limit cycle is, it's where we have the regular old cycle, but with an interesting property where if you have any trajectory that's kind of close outside of it, it converges to this loop as time goes infinity. So if you have like a trajectory that starts a little bit outside of it, it's close enough, it'll go into the loop eventually. It'll join the loop. And then similarly, if you start from the inside, then eventually it'll converge to this loop as well, or this so-called limit cycle. And so basically, if you have any trajectory that's bounded within this omega, it must approach some limit cycle. It doesn't tell you which limit cycle, there could be infinitely many, but it says that it must approach some limit cycle. Okay, so how is that exactly useful? Well, I'll explain. Okay, so as we already determined, if we have all the assumptions that we stated earlier, then no fixed points would imply that our trajectory goes to a limit cycle. We're all good on that, I assume. So then what would happen is, or an alternative way of expressing the Poincare-Bendixson theorem is that if we have instead finitely many fixed points, well, then what the heck happens to our trajectory phi? Well, an alternative way of saying Poincare-Bendixson theorem, assuming we still have all those assumptions like closed bounded omega, we have a continuous vector field, whatever, then phi can either converge to a limit cycle as expected, right? Or phi could converge to a fixed point. One of the two must be true. And what Poincare-Bendixson theorem is saying is that for a 2D continuous dynamical system or a continuous dynamical vector field defined on our closed bounded omega, only one of these two outcomes must happen. In other words, we're ruling out the existence of any other outcome. And why is that useful? Well, in dynamical systems, a lot of us dynamical systems people are concerned with chaos or chaotic behavior. So what exactly is chaotic behavior? Well, I'm sure if you've been on the internet for longer than like a day, you've probably seen like YouTube shorts of a double pendulum, or I don't know, some visual explanation for what chaos is. I don't know, you've probably seen something about it. Basically, what a chaotic dynamical system is if you have like, I don't know, a vector, if you have like an initial point x naught, you have your vector field, then we kind of already know what trajectory it'll take based on the differential equations that we have. Now, if we just perturb it just a little bit, so we say x naught plus epsilon, for example, then in a chaotic dynamical system, the behavior will vary wildly. So instead of so in a normal dynamical system, non-chaotic, it'll follow the path of the x naught, the original, pretty closely. But in a chaotic dynamical system, it could end up like this. Okay. Yeah. And so essentially, the hallmark of chaotic behavior is something called a chaotic orbit, which it's a bit more complicated to explain, but just know that convergence behavior, chaos is a completely separate category that is defined on dynamical systems that are for 3D, continuous dynamical systems that are only 3D or higher dimension. And there's a theorem proving that the minimum dimension for chaos is 3. But for the 2D case, only one of these two outcomes can happen. We cannot have chaos. In fact, chaos is important. You know, I'm actually proving the existence of chaotic behavior in actually a machine learning algorithm called RMS-prop. That's for one of my research projects, and so it's actually a very relevant subject. And so it's actually quite huge that someone managed to prove that we can't have chaos in 2D. All right, well, thank you for watching. I hope you stay to watch my other YouTube videos, which I'll be trying to post more regularly, but we'll see. Anyways,